Hello everyone, and welcome to this session where we break down a classic physics problem. Today, we're going to investigate how much a basketball rim resists deflection when a player hangs from it. This problem is a great way to understand forces, equilibrium, and the concept of elasticity, which has applications everywhere, from designing bridges to building shock absorbers. Let's dive into our problem. We have a 110-kilogram basketball player hanging motionless on a rim, which deflects downwards by 15 centimeters. We need to calculate the force constant, often denoted as K, assuming the rim behaves like a spring. First, let's visualize this. Imagine a simple diagram: a basketball player hanging vertically from a rim. The rim itself is bending downwards. There are two main forces at play here: the downward force exerted by the player's weight and the upward restorative force from the rim trying to return to its original position. We'll mark the player's mass, m, and the distance the rim deflects, x. Now, for our key variables and constants. The mass of the basketball player, m, is 110 kilograms. This mass under gravity creates the downward force. The deflection distance, x, is given as 15 centimeters. It's crucial to convert this to meters for our calculations, so x becomes 0.15 meters. This x represents how much our spring, the rim, has been stretched. The acceleration due to gravity, g, is a constant, approximately 9.81 meters per second squared. The force, F, acting on the rim is the player's weight. And finally, K is the force constant we want to find. It tells us how stiff the rim is, or how much force is needed to cause a certain amount of deflection. Since the player is hanging motionless, this means the system is in equilibrium. According to Newton's first law, if an object is not accelerating, the net force acting on it is zero. In our case, the upward force exerted by the rim must exactly balance the downward force of the player's weight. The relevant equations are: 1. The force due to the player's weight, F equals mg. This tells us the total downward force. 2. Hooke's law, F equals kx. This describes the restorative force of a spring, which is proportional to its deflection. Let's do the calculations. First, we find the player's weight, which is the force F acting on the rim. S equals mg is 110 kilograms times 9.81 meters per second squared equals 1079.1 newtons. So, the player exerts a downward force of approximately 1079.1 newtons. Next, we use Hooke's law, knowing that this force F is balanced by the spring-like force of the rim. F equals K times X. We want to find K, so we rearrange the equation. K equals F over X. Now, substitute our values. K equals 1079.1 newtons divided by 0.15 meters. K equals 7,194 newtons per meter. So the force constant K for the basketball rim is approximately 7,194 newtons per meter. Let's quickly check our answer. The units are newtons per meter, N, which is exactly what we expect for a spring constant. Force per unit length. The magnitude of K is quite large, which makes sense because a basketball rim needs to be very stiff to support a player without excessive deflection. If K were very small, the rim would deflect a lot more, perhaps even touching the floor. This result seems consistent and accurate. In conclusion, by applying the principles of equilibrium and Hooke's law, we determined that the force constant of the basketball rim is 7,194 newtons per meter. This value quantifies the stiffness of the rim. Understanding force constants is crucial in engineering, allowing us to design structures and components that can withstand specific loads without deforming excessively or failing. This concept is fundamental to understanding how materials behave under stress, and it forms the basis for more advanced studies in areas like material science, structural analysis, and even the study of vibrations and oscillations. Some additional insights. Our approximation of the rim as a simple spring is a simplification. A real basketball rim has a more complex structure involving bending and torsion. However, for a static, vertical deflection like this, A simple spring model provides a very good first approximation. If the player were bouncing, we'd need to consider dynamic forces and energy concepts, which are more advanced but build directly upon these fundamental principles. In summary, this problem beautifully illustrates how we can model real-world scenarios using basic physics principles. We saw the importance of identifying forces, understanding equilibrium, and applying Hooke's law. These are foundational concepts that will serve you well in many areas of physics and engineering. Thank you for joining me for this session. If you found this explanation helpful, please consider liking this video, sharing it with your friends, and subscribing to the channel for more physics and mathematics problem solving. Feel free to leave any questions or comments below. And if there's a specific problem you'd like to see solved in a future video, you can donate to the channel, and each month we'll select a few viewer-requested problems to solve in their own dedicated episodes.